Good day, dear colleagues. Thank you very much to be here and to join to our conference, offline or online. And first of all, uh, I want to give word the head of our laboratory um, of polymer biomaterials and systems, Mika Kartunen. Can you put him on the screen? Hi, Mika.
Hello. Okay. Do you see me?
Yes.
Oh, you hear me. Okay. All right. Well, good afternoon, everyone. It's morning here, so let me see if I can share my screen here. Here. Oh, you see my screen? I can see myself. Okay. There you go. All right. Welcome everyone to this international conference on new approaches to biomaterial development. It's with exceptional circumstances, so we are in hybrid mode, uh, in person in St. Petersburg, and then the rest of us are online. And since we have speakers on both sides of the Atlantic, the time is a bit unconventional. So 16:20 Moscow time, or St. Petersburg time, and 8:20 in the morning here across the ocean. So first of all, I'd like to acknowledge the people there in St. Petersburg for organizing this thing, even at these difficult times. The original plan was, of course, to be in person, and at the St. Petersburg and Sergei Liulin, Sergei Larin. Big thanks, and especially to Dmitry Tolmachov, who did a magnificent job in putting everything together despite short time scale and all these difficulties. And it's a lot to do with his big efforts that we are here. So let's get started. For those who have not been in St. Petersburg, so let's take a look where we would be. So basically, this conference is one in a series, and the previous one was actually in summertime, pre-pandemic. So let's just to give you a little taste. If you haven't been here, so this is the Vasilievsky Island in St. Petersburg, the IMC, the Institute for Macromolecular Compounds. And the host is in this building here. This is the old stock market building in St. Petersburg, and this is the place where everyone goes to take wedding pictures, if you like. And those who are in person, they are up here right now in the hotel, in the conference hall of the hotel. And of course, the Russian Academy of Science goes back to 1724 when Peter the Great founded it. And actually, his advisor was no one less but Gottfried Leibniz, so the famous person from who also discovered the differential equations together with Newton. And Mendeleev worked here, so this is the University of St. Petersburg buildings, so right next to the IMC. The Hermitage Museum is just across the bridge here on the other side. So it's really a central location, and maybe the most famous scientist from the early academy time is Leonhard Euler, the Swiss mathematician who did most of his career in St. Petersburg. The Euler Institute is basically across the river on this side. And I suppose, I don't know if it's a winter time there, but to give you a taste of how it looks like, since we cannot be there, I'll run these movies that I picked from the internet. These drones do a fantastic job. So hopefully next time for the next edition, we'll be able to be in person. So this is exactly the same area. So this building here is the location. There you go. So this is how it looks like there. And and like I said, hopefully this pandemic will be over soon, and we'll be back to more normal time. But unfortunately, right now, this is where we stand. Very good. So we are almost ready to start the first session, and we have an exciting lineup of speakers. from, of course, locals, then guests from North Carolina, Prague, France, Finland, and hopefully Brazil. We are having slight difficulties in that, but we will see how this goes. So the first speaker of today will be a computational talk that will be given by Dr. Hector Martinez Seara. He's from the Czech Academy of Science. And this is quite exciting stuff because for simulations, so this conference will be a combination of simulation experiment. For simulations, simulating charges, salts, charge groups in molecules, it's a big challenge. And the past few years have brought this problem even more into the attention of people, seeing things such as overbinding and such. And Dr. Martinez Seara has worked a lot on these problems, and he will be talking about possible solutions today. So I think with this, I'll stop the movies here, and I give the word to Dimitri, and I think he will be chairing this session. So thank you very much, and I hope you will enjoy the conference.
Thank you very much, Miko. So, as Miko Kartonen said, the next speaker is Hector Martinez Seara from Prague. We can see your presentation, Hector.
Perfect. Can you see my mouse? Okay. Well, thank you, Miko. It was a pleasure to be invited again to this series of talks. And as you have said before, my talk will be mostly theoretical in the computational part. But I think that this is a materials talk. But many of the things that I'm going to explain here, I think they're extremely relevant when it comes to simulating materials, because most of the materials are actually of interest, are highly polar in many cases. They have charges in the surface. And when you deal with all these parts together, having the interaction right, at least when you are using classical simulations, it can be a bit tricky. And here I'm going to talk about biosystems mostly, but many of the lessons that we are applying now here comes from the study from more simple salts in solution. And we believe that this is something that it's actually can be expanded to many other fields. So anyway, what I'm going to talk today is like a new force field that we have developed for the last 4 years, and it's based on Charm36. And this force field, we call it Prosecco. And the only thing we have done in this force field is to reintroduce one part that is the electronic polarizability, which is missing in non-polarizable force fields. And I'm going to explain why we did that, what is the advantages and how we do that, and what are the costs. So anyway, just to give you some background on why I'm interested in this is what is my background, is membranes. And membranes are a bunch, not only lipids like the people think, like cellular membranes, but they have proteins, they have sugars around, they have ions, they have plenty of stuff. And all this stuff interacts one to each other. And the only way that we computational people can study these things is by getting right all these interactions. For example, let's think about a simple, very simple membrane when there are only 20 components. I can tell you that that has nothing to do with reality. In reality, you will have hundreds or even thousands of components simultaneously interacting. But even in these simple systems where you have kind of like 10 lipids, a bunch of 6 proteins, few ions like sodium, calcium, and the water that is everywhere, these 20 components will give you the astonishing of 210 interaction parameters, only if you can define it by a simple interaction. So this is already started being mind-blowing. And what we are doing, and in order to get the membrane, this complex membrane right, we need to get all these interactions right. In many cases, we have always traditionally hoped that by making some interactions between this ion in water and this protein with another protein, then when we mix together, the ion and the protein will also interact correctly, and everything will nicely fit and give us prediction capabilities. And the truth that we have been very optimistic and very successful, but unfortunately, that's not always the case. And sometimes there are interactions that we have missed on the way. So in order to be predictive, we need to be quantitative. And actually, one of the things that I'm going to say is that traditional classical molecular dynamics, force field molecular dynamics, have at least one shortcoming. And this shortcoming is the missing electronic polarizability. So what I mean by electronic polarizability, when we have classical molecular mechanics, we have like balls, and with these balls interact. And one of the properties that they interact, if they are charged, they have some sort of thing that's called partial charge. And the partial charge, which is not a real observable, it's somehow like this 0.5, this minus 0.5, so they attract. And they attract based on the Coulomb law, that's what you have here. But please notice that in the Coulomb law, there is one part which is the electric of the medium, and this the electric constant basically can be divided into contributions. One is the nuclear contribution, which accounts for a lot when you are in water, is 45. And then you have the electronic contribution that it's smaller, it's 178, but still that will make that the force is halved. So it's not that it's like negligible, it's just smaller, okay? So let me start with the nuclear part. What is the nuclear part? Well, it's simple. You have two molecules of waters like this one, and the oxygens are pointing to each other. Both of the oxygens are negatively charged. So if you run here a dynamics or a minimization, naturally these waters will try to reorient so that what will form is the hydrogen bond, which is a negative charge interacting with a positive hydrogen, let's put it that way. And this actually, molecular dynamics is extremely good capturing this movement during the simulation. So it always tries to minimize this electrostatic interaction. So this, it's really nice. What happens is that the other part, is 178, it's not there. We don't have electrons. So we don't have it. We don't have a Drude. We don't have anything to try to mimic this behavior. So this 1.78, it's always going to be missing. And what does this mean? Nothing. No, actually, that's what we thought. But we have started finding more and more relevant cases where this is actually important. Let's imagine a membrane. What we see here is a membrane, POPC membrane, and the gray balls basically are calcium. What we realized very soon is that when we are using this non-polarizable force field, this calcium was attached to this neutral membrane even extremely strongly. It was just going there, never to move again out. When we are able to introduce this electronic polarizability, I'm not going to explain now here, I will explain later. What we see is that the calcium doesn't bind that strongly anymore to the membrane. And actually, that's more even natural, because otherwise we'll have seen somehow in some technique that the membrane is fully covered in calcium, because that's what was happening in the simulations. Another example which has not to do with membranes, has to do with proteins. We have here a protein which is called calmodulin. This calmodulin, it's a very interesting protein, it's a second messenger, and interacts with, binds 4 calciums during its functional and signaling. The issue is that when we simulate this protein in water solution, and we add calcium to the medium, the protein just gets full of calcium everywhere. Of course, there is a lot of calcium here, not biologically relevant concentration, but that's what happens. And the question one asks, why nature need to spend so much time creating very well-crafted loops to bind calcium if it can bind calcium anywhere? It can bind 20 calciums. You can see here in the lower part, this red peak when we put here. So again, when we add the electronic polarizability, what we see is that all these calciums goes away, and we get the calciums only in the loops where they have to be, and few more that bump in and out, but it's just more like dynamic. So we get the proper behavior of the calmodulin. Again, now we recover the core behavior, and that's only by introducing this missing a small part. So let's see what happens. So as we said before, the charges in the electrostatic interaction in MD simulations are basically the Coulomb law. And they only depend on the partial charges, and they are minimized by reorientation. This reorientation is a slow process. It takes time to reorient. Of course, you can think the water reorient very fast. It still is not immediate. It takes time. It still accounts for a lot. And actually, simulations definitely, they can solvate ions, so it works. But we are missing still the electronic polarizability. This electronic polarizability is instantaneous. That means that this 1.78, even though it's small, it's going to be there all the time. So 2 interactions will always be screened. So you will have the interaction halved, essentially, to some extent. And basically, that's what we see in this equation here, where we can actually add the electronic polarizability as the electric continuum of the medium. And if we do that, and we actually split into parts and add one of the square root of the electronic permeability, we can actually add it to the partial charges. Or what we are seeing the same, because by luck, we have that the electric constant the electronic part, is 178, 1 over the square root of this 1.78, it's by chance 0.75. So by multiplying the charges by 0.75, you effectively, in a mean field way, are creating this screening, and you are reintroducing this missing electronic polarizability. And the good thing is, because now we have only a new charge, essentially we're not putting extra terms to our force field, not making more complicated, more demanding. We have just zero cost. We just go compute this new charge, put into our model, we are done. So this, of course, is easier said than done, but it can be done. So we are going to do that with CHARM. Why CHARM? CHARM is a state-of-the-art force field. It covers a large number of biomolecules. It's modular. That's very important for us. It's like a Lego. You can put pieces, and each of these pieces actually has charge, which has an integral -2, -1. This is important for us because, unfortunately, charges are not observable. And therefore, it's not that we know which is the charge of an atom. We cannot know that. And then we have to scale everything, because that's the only thing that the theory tells us. But the ECC theory doesn't tell us how we have to develop these charges. It only tells us the full charge has to be the global charge, which is real, divided by 0.7, multiplied by 0.75. So when doing that with CHARM, we have taken what we call a minimal damage approach. And we do that because CHARM has been, force field has been developed over many years. It has been carefully crafted to make well certain interactions. So we don't want to mess with them. We don't want to mess with the secondary structure of proteins. We don't want to mess with interactions of certain lipids. That this, we want to keep it as much as possible. But the interactions in the charge groups, we want to improve them, because that's where this is more apparent, this missing. So we only scale charge groups. We also have to study the ions, because we have ions which we believe they are better, and they are better in the context of this DCC. And we have to disable this MV fix that they have pushing in the CHARM people. That basically, that's the same correction we want to do, but instead of having some physically sound correction and explain, the only thing they do is like saying, okay, we know that the charge interacts too much, so let's push them out. And of course, they don't interact. However, the question is what happens if the charge actually has to go there at some point? It can't anymore, because you are pushing it out. So basically, the MV fix works well in terms of these interactions, but it destroys the potential complexation and another chemical phenomena that could occur. Anyway, in all these molecular groups, we'll have then a fractional charge like 1.75, 0.75, 0, minus 0.75, or 1, minus 1.5, for example. So this is what we are going to do. So now that I explained what is this, let me explain where we have done that. So far, we have done that a lot in ions. So it's something we have well covered. Now we have introduced it to lipids, sugars, and proteins. And with this, we believe we cover most of the major macromolecules. We have DNA still in the background. We are actually working on that, but that's going to take much longer, because DNA is very complicated. So let's see what happens when we do this scaling for lipids or for the membranes. So these are the two molecules that I'm going to concentrate more: POPC and DP. The POPC, you can see here the molecules, but we are going to talk also about PS, which is a serine group. So when we are doing the scaling, basically what I'm scaling is the things, the atoms. These are the head groups of these two molecules. That's the only thing we scale. And we only scale the parts which has been colored here. I'm not going to go in detail, but trust me that now the choline group has a charge of plus 0.75, and the phosphate group has the charge of minus 0.75. For the serine, which is on the right side, you will have actually that additionally, the carboxylic group will also have a charge of minus 0.5. So let's see what happens when we do this, and we try not to mess with anything else. So first of all, let me explain what is this graph. In this graph, it's the only available data, primary data we have about how membranes are. There are other data, but they are much more difficult to relate with structure. Of course, you can make correlations to this. This is NMR order parameters of the head groups at the top, on the tails, on the middle, and then we have Sachs and Sands data with scattering, that we can see how it behaves with respect to experiments. So with the black lines, basically are the experiments. With the red lines, we have the original CHARM 36. And what I want to transmit to you is that when we make changes, when we make these Prosecco changes, these changes of scaling, our data either behaves in the same way, equally well than CHARM, or it improves it. So how we see that? So the black dots should be closer to our red, to our blue dots. It's not always true, as you can see it here, so I'm not going to say. But in most of the cases, if you see, basically the lines are one on top of another, if you see in the sacs in the lower part, or it's very similar. We get a bit more compressed data, and actually we know why, and we might solve this in a future expansion. But essentially, the membrane behaved the same way in Prosecco that in Char36, and that was our main important thing, because we only want to change the interaction with ions. Then the second thing, now we check the interaction with ions. The interaction with ions is very difficult to analyze, and that's why traditionally was not the focus of attention. Actually, that was done a long time ago. It was in the 60s when Sealing actually started making a series of experiments of NMR, or calculating the NMR of the parameters, a function of the concentration of ions. This data got buried, and actually a colleague of ours, Samuli Olila, uncovered it and realized that that's actually the data we need to parameterize the interaction in between the membranes and the ions. And that's something which I think is very important for the community at this point. So again, Prosecco is the blue line, the black line is the experiments, and the rest are either the charm with the MBFix or the non-MBFix. And as you can see, the blue line systematically gets closer as a function of the concentration. So when we measure these order parameters as a function of the concentration, the blue line gets closer to the black line at all moments. Please notice the red line. The red line is when there is no attempt to do anything to correct this problem, especially in the rat side with calcium. The red line follows down and this is actually the sign of these calciums attaching to the membrane and never leaving that I comment at the very beginning. So we need to do something in order to even qualitatively resemble what the membranes will do. If we want to go quantitative, then again, Prosecco is actually quite good, or at least better than MBFix in this case. We have the same with POPS, and POPS is a negatively charged lipid. And again, our blue line gets much closer to the black line. Again, we are improving respect to the original charm, and I think that's good. We don't make it perfect, just to be clear. If you go to the right side or for the PS, the left side is a POPC, POPS mixture, so it's that the POPC, so we are doing well, but we are not doing perfect. When we go to the PS, which is on the right side, actually we see that, again, we are getting closer in the upper panel for the beta carbon, but for the alpha carbon, actually, we are still not doing totally okay. But we are still improving substantially the response that we are observing. Here we have a binding assay as a concentration and the ions, and again, the black line is the experimental and the blue line is the Prosecco. Compared to non-using MBFix or using MBFix, our response is also better of the binding of ions to a membrane. So again, we are improving. So what about the dynamics? As I mentioned originally, and that's what you see on the left side, when the calcium bond, it was staying there. That's why you have resident times of 2 microseconds. That's what you see in the left panel in red bars. When the people introduced an MBFix, this was reduced basically to 5 nanoseconds, like go back, go back, go back. Now with our Prosecco, we have a more natural decay. However, I have to admit that we don't have any data to know whether Prosecco is a good profile or charm MBFix is a good profile for the dynamics, because this data does not exist, at least experimentally, as far as we are concerned. Then we can also check how these ions that attach to the membrane, how many lipids they complex to each other. And again, the complexation numbers could be 1, they attach only 1 lipid, 2, 3, or 4. With the lipid force fields where there is no any attempt to correct this electronic polarizability in any way, then you have that it attached to 4 lipids and it actually makes a complex very strong. That's why it gets attached and never leaves. As soon as you put the MBFix or the Prosecco, you go more to single lipids or a couple of lipids. And actually, there is some hints on the NMR data that the 2 and something is the number magic of the attaching around 2. So actually, we are better, but still there are some fitting models in this, so you have to take it with a lot of careful. And then one other thing we have done is sugars. Sugars are everywhere surrounding proteins. They are by themselves in the glycocalyx. So there are very important pieces, and some of them are charged. I'm not going to go to much details, but most of the charges are either galacturonic sugars or glucuronic sugars. Both of these sugars, actually, here you have the osmotic coefficient as a function of the concentration of this sugar, and you can see that the blue line again is much closer to the black line than the red. Please notice that it's on the top. So if without the correction we are below, and now we are overshooting a little bit. We are aware of this overshooting, and actually I think it in all the force field. But again, it's something which we are aware and we are working, because I think we even understand why it's overshooting. So we will make we are working for a new generation of the Prosecco, where we hope that this will be put in the correct place. Okay, and this is happening for both these galacturonic, glucuronic, which are typical sugars that are found in heparan sulfate, hyaluronan, chondritic sulfate, all them as glycans and very relevant in biosystems. So what about proteins? Proteins the same. There are, of course, in proteins there are 4 amino acids which are charged. Histidine can be charged as well, but we are only working with the 4. And this is the primary targets of here. When we are actually making the scaling, first I want to show that by making the scaling, we are trying very hard not to disturb the backbone, because this has been tuned a lot. So we are not trying to decide if it's good or bad. We are only saying that we don't want to change the one from charm, because that will require a full optimization. So we can see here, we can make a D-lysine, D-aspartic, D-arginine, and D-glutamic. And in all these 4 charged amino acids in the peptide, we see that the profiles we are getting from the phi and C angles basically is the same. Therefore, it means that we are not changing a lot, at least this. I'm not saying nothing, but I said we are not changing a lot. So we hope that this is actually acceptable, the changes. One other thing, and now this compared to experiment, because the other thing is just simply compared to the original chart, we see again, if we make the simulation of the osmotic coefficient of these amino acids as a function of the at certain concentration, and the experiments of this osmotic coefficient, if we do it with the charm 36 without the electronic continuum correction, we see that we systematically we are below the line. Okay, and instead that means that the interaction is actually too strong. When we go with our Prosecco, we go much closer to the line, which is this black line, which is placed. However, we are overshooting. Again, the same thing that happened in glucuronic. And as I mentioned, we think we understand why it happens, and we are working on correcting it. So now we have sugars, we have proteins. So what happens when we put this together? This is only example, and I put it because we were amazed. What happened? We have this this protein membrane interaction is the PKC alpha the C2, and this protein is able to interact with the PS membrane via a calcium. So if you put the normal charm without not MB fix, and you put this protein with the membrane and the calciums, you will see that basically it doesn't bind. It stays around, nothing else. When you put MB fix, actually the protein managed to go, but it binds in a very weird way. When we make the ECC, and I promise you, we were as surprised as anything, it just goes to the membrane, recruits a calcium, and it binds in the current binding site. And this is what you basically see on the right side. There is this part, you can see where is the position. On the left side of the position, red in the full charges, then when there's MB fix, which is there in the membrane, but not in the correct position. That's why the peak is displaced. And with the scale charges, you can see that it's very similar to the dashed line, which is the position in the crystal that is checked. And actually, if you actually put the crystal together with the conformation we find, is nearly identical. So we were absolutely amazed. Notice that there are 2 calciums. So the probability that that was a random thing is it's impossible. And by the way, we did not put the guy there so that it stays. It just came itself. And for that, this is basically what I'm showing here. We put here the PKC alpha, and at some point the calciums appear. They are only shown when they are close to the binding site. It's not that they are there and appear from the nothing. But as you can see, they form and they stay. So actually, we believe, and this only happened with Prosecco. So actually, we are extremely happy. And with this, I would like to finish with acknowledgements for the people who has done the work, in particular for the lipids, is Ricky Nensini, was my master's student at that point, and we are now finished the paper with him. Then for the proteins was originally Pauline de Croix, who started this, but now they have catch many other people like Carmelo Tempra, Matti Javanainen, and Miguel Rio Pedre. And for sugars, basically it's Denis Virukov pushing, but we have experimental collaborators, Ondo and Jan Heida, the BCGT, that are actually working hard, helping us to find comparison data. And unfortunately, I would like to dedicate this talk to my dear friend, Dr. Thomas Rock, which unfortunately passed away. For those who know it, he was a wonderful person, excellent scientist, and a person to trust. So with this, I would like to give the floor to any question. Thank you very much.
Thank you. Thank you very much, Hector. Do you have questions? Someone?
Miko has a question, seems to be.
Miko?
Okay, sure. So yeah, let me start. So can you, there's a couple of things. So can you clarify the difference between the ECC Prosecco and are they the same thing, or is the Prosecco now systematization of ECC?
ECC is some term that we used when we realized that this could be applied in general to molecular dynamics. So this is basically a general term. Prosecco is simply a force field which uses ECC approach.
Okay.
So it's basically, we are using this approach because there is no a unique way to set up the charges. It's actually up to us. The only thing it tells us ECC that the overall charge has to be 0.75. How do you reach this charge is totally up to you. And actually we are trying to work if there is any systematic way that we could use, but it seems that there is a lot of fitting still going on.
Okay, so just to continue on that, so then let's say if someone would like to use now this, is it available somewhere, or it's still under work and
now actually it's available. The parts that I presented here, all of them are available. Still, I have not made public the link because we are trying to get the permission from Charm people to put the files because we are obviously using Charm and we are not. I mean, I find myself very uncomfortable publishing things of other people in my name. So once we get the permission, we will put them. We'll disclose the link online. If you want it, still I can send. And the other part is that if they will not provide us the permission, which is possible, then we will only provide some sort of like recipes on how to transfer their files so they can be used with Prosecco. That will be much more complicated for the user, but that's the life. We cannot do much of that.
Okay, if I may continue one more thing and hold this space. Also, if you take your slide 22.
Yeah, let me share the screen again.
Yeah, so that was calcium, right?
Let me share the screen again. So slide 22, you say?
Yeah.
Yeah.
Sorry, maybe it was after where you have the protein and the membrane, and you. Oh yes, exactly. Sorry, it was that. Yeah, sorry. Go back. This is the movie. So if you go back to the previous one. So why on earth does the calcium not catch the membrane with the protein with the full charges? So what's your explanation?
My explanation is, first of all, the problem I think is that in full charges, the PKC does not want to approach even to the membrane. That's actually we have found in many proteins which are actually positively charged overall, that they don't want to approach the membrane at this point. Sorry, negatively charged in this case, because that's a PS membrane, probably I forgot to mention. So the calcium actually helps to overcome this barrier in this case. So it is a balance in between the amount of calcium you put that overcharges the membrane to positive, and actually that the place that it has to bind is actually also positive. So it's not going there. Sorry, it's positive actually. I said it correctly the first time. So it doesn't want to go there because then it gets basically, there is too much things going on below me. So I cannot go because to charge. And this is basically, there is a subtle balance. It is the only protein which I'm aware of that binds to the membrane via PS. There are many other proteins that bind to the membrane via calcium, but it's the PIs that they are doing this job, PIPs. That's the only protein we are aware, and that we picked that because it's more subtle, the binding. And we were, just to be clear, we have two replicas, all of them go to the same place. And we have replicas with the other. With MBFix is clear, you cannot go because basically the calciums are pushed away. So there is no way that the calciums can go inside. That's what I mentioned about the complexation. In the case of full charges, the problem is that anyway, any calcium that we put goes to the membrane, stays there forever. And then the protein doesn't want to go there anymore. So it stays floating around saying like, look, you have too much positive charge actually now below.
Okay, thank you very much.
If I may, I have one question about NBFix parameters. It's technical questions. As I know, in chapter 36, NBFix are implemented. There is no NBFix model of calcium, and this was publication of after
work, some of them that we have done with you. With charged force field, seems to be extremely easy to predict what is happening when you make ECC. It seems to decrease these interactions with the charged moieties, and that goes usually in that direction, no matter what. With other force fields, in particular amber force field, actually it's more a gamble. You actually decrease the interaction, or you decrease the charge of these groups, thinking that the interaction will be decreased, and you actually see the completely opposite effect. This is not entirely surprising compared to the MB fix, which is always tells you what is going to happen, because the problem is that you decrease the interaction between the two charge groups. It doesn't mean that there are other interactions with other molecules in the system, and how how all these interactions place together, it's not deterministic. And actually, we know it now. To be fair, when I started, I thought that was not the case, but now I know that that's actually very normal. And in particular, amber force field, which is the other major force field used for biosystems, I will say that because of the way of constructing the partial charges, which are much more delocalized, it looks to us, it's like this ECC was already implemented to some extent. Therefore, it makes that when we are trying to do that on their systems, we are actually doubling it's like scaling what is already been scaled. It's not exactly that, but it is mostly in that direction. Still, we don't have, as I mentioned before, a golden rule of what should be the partial charges to which we could apply without sweat the ECC on top. This is something which we are actually trying to guess. This is one of the parts we are trying to researching, but so far we have not found the clue how to tackle this problem.
Thank you.
Okay. Thank you very much, Hector.
Thank you, Sergei, by the way, that I see a couple of them. So, and thank you for inviting. See you.
I would actually have one question if I can still ask.
Yes, by all means, Maria.
Yeah. So how would this go for an apolar solvent? Because you are now scaling the charges in aqueous solution.
Yes.
And we are working with some rather apolar hydrocarbon solvents and oils.
That's an excellent question. And I will tell you the following. It's way more important.
Yep.
Because here in this, as you can see, the nuclear part here is 45, which basically shields a little bit this 1.78. But if you are, for example, in a completely apolar solvent where the nuclear part, like methane, imagine that you have liquid methane, for example, just putting the more extreme thing. Here you will have a 1.01 actually. At that point, the interaction in between anything with this charger, it will be kind of like the electronic part halves by 2. And then we are talking about the difference between 400 kilojoules per mole for two charges, to sodium and chlorine, will pass from 400 kilojoules per mole to 200, rough numbers. This is actually much more important. So what we are showing here is that in water, where this is relatively very mild correction, plays a big role in these interactions. If you have apolar solvents where this 45 gets gradually lower and lower and lower, this correction plays a larger and larger role. So definitely, by all means, this is something that you need to account for apolar solvents.
Thank you very much. Yes.
And just to be clear, one thing, this 1.78 here is not water. Everything which is constituted by the elements of the first two rows of the periodic table will have a very similar thing. Methane, actually, liquid methane, has a value which is 1.69. And other things that you will find will be in this order, 1.69, 1.79. It will be really in a very short range. So these scalings are actually quite general, and you don't have to rescale for everything single solvent. This is something that we can actually do, and we are working actually in these apolar solvents. We are working on them because of that.
Okay.
So, any further questions?
Any more questions? Okay, so thank you very much again, Hector, and we will move to our next speaker. The next speaker is Sergei Shaiko from North Carolina. I'm sorry.
Yes, hi guys. So shall I share my screen? Okay. So can you see my slides?
Yes, we can see it and hear you.
Okay, very nice. So yes, good morning, good afternoon, good evening. And yes, thank you for inviting me, and it's a pleasure to present our research. And this will be, my talk will be about engineering of materials or tissue mimetic materials for reconstructive surgery. And this will be based on so-called brush-like, or sometimes people call them bottle brush macromolecules. And these molecules are relatively stiff because of this steric repulsion between multiple and densely grafted side chains. But if you put them together and connect and make networks, you get very soft and tissue mimetic networks. So, and the concept of what we're doing is relatively simple. So talking about reconstructive surgery, or in general, any type of implants could be also used for drug delivery. So let's say we take a syringe and you have a certain formulation, you inject it into the body. And initially this formulation is fluid. But as it reaches the body and reaches a temperature, let's say 37 degrees, then inside the body it will cross-link and become an implant or tissue mimetic implant. And important that as it cross-links and become it can be elastomer, or it can become a gel. And important is that it would match the mechanical property of the surrounding tissue. Basically, it kind of mechanically blend with the surrounding tissue. And in addition to blending mechanically, also we would like to control water fraction, because the water fraction in tissues is constant, is about 70% water, about 70% water in the tissue. And we would like also to make sure that our materials would have not the same, but let's say controlled water fraction. And we will talk about different type of networks. It could be chemical networks, so covalently connected, and also physical networks. And yes, there is a pros and cons. If you talk about chemical networks, they're very robust, mechanically robust, stable. But because of chemistry, cross-linking chemistry, they may include some residual chemicals. If you talk about physical cross-linking, it's very nice. I mean, there is no any side products, but they're mechanically fragile. So this we need to keep in mind. And we will talk about two systems. One would be elastomers. It means there is no solvent. Still, they will have a tissue mimetic mechanical properties. And the second system, we will talk about gels. And if you talk about gels in particular, one of the challenges here would be decouple swelling ratio and mechanical properties. In conventional synthetic networks, these properties are coupled, because if you, for example, increase cross-link density, then you will make networks stiffer, and also you reduce swelling ratio. These parameters are coupled. But if you take, for example, tissues, like you consider fat tissue or skin tissue, so they have very different mechanical properties. Difference in mechanical properties will be, let's say, 4 orders of magnitude between fat tissue and skin tissue, but the amount of water is the same. So the nature knows how to control mechanics and composition independently. All right. So, but first we'll talk about solvent-free systems, and this is what actually was, let's say, if you about 3 years ago, as we started this project, initial motivation, we wanted to get rid of gels. We don't like gels because for 3 reasons. First of all, gels are brittle, as you see here. Second, gel mechanical properties do not match mechanical properties of tissue. And as this is shown on the right-hand side, for example, if you take a tissue like fat tissue, if you specifically talk, for example, about breast tissue, which is effectively it's fat, and initially it's very soft here, very low modulus. So this is what we measure, stress versus elongation. So initially it's very soft. But then fat tissue, like any tissue, becomes increases modulus. So this is what we call firmness or firm tissue. So and you can easily check it just yourself. I mean, for example, you take skin and you just pinch yourself, or first you touch yourself, and you see that your skin is relatively soft, and which is very nice, and we very much appreciate the softness of our body. But then if you try pinch yourself and pull the skin, you will see that actually the skin becomes very stiff as you pull it. So this is what is shown here. Initially the slope, which is effectively Young's modulus, is relatively low. So it feels very soft at small deformations, but then as you stretch it, all tissues increase their modulus, and they increase this modulus is not just by a factor of 2 or 3, they increase modulus by 2 or 3 orders of magnitude. So it's a very significant effect. It's called strain adaptive stiffening, or I mean, using common language, it's called firmness. So the tissues are simultaneously soft and firm. But if you take materials which are currently used, for example, specifically for breast implants, they're soft and they remain soft all the time. You keep stretching and stretching, and they basically the modulus doesn't change. And this is what it's not good for. This is not a good material for implantation, but currently there is no other materials. And the third property which we do not like in gels, it's just liquid fraction, and it's and because liquid is always it's a loose material. It can leak. It can leach. It will leach into the body. It can evaporate and or phase separate. And you can easily demonstrate by take, for example, this piece of silicone gel extracted from this breast implant, put it on the filter paper, and you see that as a function of time, you see it clearly. You see this leaching. And this is exactly what happens in your body, and people know about it. But people do not like talking about this, but it's very well known that after a couple of years of implantation, you found this silicone oil in lymph nodes. So it's very well known. Anyway, first we became interested in solvent-free materials, but with tissue mimetic properties. So how we did it, and this is shown here, effectively on the left-hand side is gels. You see the solvent molecules in polymer network here. On the right-hand side, we effectively, what we did, we replaced solvent molecules with side chains. And so effectively, like materials dissolve in itself. And what you see is that the dramatic difference in mechanical properties. Hydrogel on the left-hand side is very brittle. And our material, which is bottle brush elastomer, absolutely solvent-free, and it's very resilient. So you can compress it by a factor of 10, and there is no any fracture. But this is not the most important one. The most important is that if you take, for example, hydrogel and leave it on a desk and come tomorrow morning, this hydrogel will become a hard plastic because of water evaporation. So if you take our material and come, let's say, 100 years later, then you will find the same material, because our material doesn't change properties. It's completely invariant, and because there is nothing to leach, nothing to evaporate, so it's a completely solvent-free, fully conjugated system. And also, naturally, I mean, as we would expect, this material doesn't show any leaching, which is again shown here on the left-hand side. This silicone gel, and on the right-hand side, the silicone bottle brush elastomer. And yeah, I want to emphasize the mechanical properties of modulus, the softness of both materials are identical. The modulus is 1 kilopascal, but mechanical properties, resilience is very much different, and also in terms of leaching, these are two different materials. All right, so this is number one. So second, what we realized as we obtained this tissue-like, I mean, in terms of softness, elastomers, then in addition, we realized that using this brush architecture, you can actually program mechanical response. And specifically, we talk about, we developed chemistry where we can control 3 architectural parameters independently. This is NSC, which is the degree of polymerization of the side chains, and G is the degree of polymerization of the space, a backbone space between the side chains. Effectively, it's a grafting density. And then X is the degree of polymerization of the backbone between two crosslinks. So we have these three parameters. And again, we develop chemistry which can control these parameters independently. We can basically put any number here. This is our architectural code. And on the right-hand side, what you see, it's a stress strain or strain elongation response or curves. And these symbols here corresponds to real tissue. For example, this circles is a stress strain response of a lung tissue. And then this blue curve is our silicone elastomer, bottle brush elastomer. And in these brackets, you see these parameters which correspond to the specific architectural code. The first number is the degree of polymerization of the side chains. The second number is the degree of polymerization of the spacer between side chains. The third number is the degree of polymerization of the backbone here between crosslinks. So if you take this, if you change these parameters, for example, you instead of 189, you will use 18, and spacer instead of 1, it will be 2. You will get a completely different stress strain response, which would be very close to jellyfish. And you can do the same, change architecture further, and you can get the mechanical response of an artery. And important here is that as we do this variations of architectural code, we do not change chemistry. So it's the same chemical composition. This is what is very important to emphasize. The chemical composition in this control of mechanical properties is a kind of secondary. The primary is an architecture. So the mechanical response is controlled by architecture. Chemistry comes second. All right. And this is how it works technically. This is how we do this. So for example, we take a lung tissue, and we measure stress strain response. This uses the symbols here. Then we take our equation of state, which is stress versus elongation. Elongation is lambda, and this is stress. And we have two fitting parameters. This is G and beta. And these two fitting parameters, basically G is our modulus, and beta is called strain stiffening parameter. Basically, it characterizes how much the modulus increases with deformation. So you have these two parameters. So, and then you feed this experimental curve with these equations. This would be this red line. And you extract these two fitting parameters, G and beta, which is shown here. And the unique kind of feature of this model, it's not a phenomenological model, it's a molecular model. So these two fitting parameters, G and beta, we know exactly how these parameters correlate with the architecture. Basically, we have equations here. We solve these equations to find this architectural code. And then the next step, we simply go to the synthetic lab. We synthesize a brush-like elastomer with exactly these parameters. And this, we get a silicon, or it could be not silicon, could be polyacrylate, any type of polyethylene glycol. Chemistry, again, is not that important, but you will get a material which will have mechanical response stress strain curve exactly, almost exactly matching that of lung tissue. So, but it's already will be synthetic material, but if you touch this material, if you squeeze it, it will feel like lung tissue. And it's again important to emphasize that what we do, we not only we just match or replicate the modulus, initial slope of this tissue, we replicate the entire stress strain curve. This is very challenging. Replicating modulus is relatively easy, but replicating the stress strain response as a full stress strain curve is quite challenging. So the next step, since we talk about materials for reconstructive surgery, we would like to make it injectable, and which is minimally invasive, of course. So what in this syringe, what you see, you have a formulation, and this formulation doesn't have any solvent. It's fluid because it's melt. But after injection, as we speak, you see that the reaction starts in material crosslinks, and this liquid converts to a piece of elastomer. This elastomer mimics property of a soft tissue, and it's a fully elastic and fully conjugated, and the gel fraction is 98%. So there is almost no solvent. It's again, it's non-leaching material, and also with this type of chemistry, we can control this curing time from seconds to hours. And this is one example of, because there is many different chemistries, but this is the way we build these molecules, and this is 3 elements. One is just synthesizes macromonomer, and it's not just macromonomer, because this macromonomer has a functional group at the end, OH hydroxyl group, which will convert to azide group here, which becomes reactive. And then you have a, then you make a bottle brush polymer by copolymerizing these reactive macromonomers with non-reactive macromonomers, which will be polydimethylsiloxane. So, and then in this way you control the molar fraction of this reactive, of the side chains with the reactive chain ends here. So we can have, for example, 5 molar percent, 1 molar percent, just give a number. And then there's also the third element would be this cross-linker. It's a difunctional oligomer here. And this as a cross-linking functionality, it will be isocyanate. But again, you can use different type of cross-linking functionalities because the chemistry is very rich. And why we do this, why we use different functionalities is just to control this curing time. I mentioned before, we can control it from minutes to hours. And here what is shown, 2 specific examples. If you have, let's say, our cross-linker would be isocyanate terminated, and the side chains will be amine terminated, it will give you 4 minutes cross-linking time. But if you take isocyanate and OH terminated brushes or side chains, it will be extends to 4 hours. And it's very important because if you do surgery and if your implant is relatively bulky, let's say 1 liter, the surgery injection usually takes about, couple of hours, and you would like that this materials remain fluid during this injection. So in this case, you would need to use this type of similar chemistry, which gives you, let's say, curing time is on the scale of, let's say, several hours. This is number 1. And second is that also for injection for injectability, we need to be able to adjust or reduce viscosity. And this you can also do with architecture. And this is where brush architecture is another, advantage. There's several brushes have several advantages for this application. One, we already talked, you have a lot of functional chain ends. And because if it would be linear polymer, you would have only 2 chain ends. Here you have myriads of chain ends, and they can be functionalized. Number 1. And second, with brushes, because for the same molecular weight, the brushes has a much more compact architecture or conformation. And in this case, viscosity will decrease significantly if you go from linear to brushes and to star-like brushes. So you see that viscosity decreases by 3 orders of magnitude, which is very significant at the same molecular weight. All right, and so now we finished with solvent-free materials, solvent-free elastomers, and materials. Again, we can mimic, we can replicate mechanical properties actually of nearly of any tissue. But then there are a lot of applications, and every time we give this presentation, and there is people ask, can you make gels? Because some applications like drug delivery or reconstructive surgery, you would like to have gels, or specifically hydrogels. So when we started working on hydrogels, and again, we would like to make them injectable also. But more important is we would like to control modulus and cross-link and swelling ratio or amount of solvent independently of each other. And currently, with the current or conventional polymer methods, is impossible because both parameters are coupled through cross-link density. If you increase cross-link density, as I said before, modulus would increase and swelling ratio would decrease. So this is a challenge. So, but first, let's say how we make injectable hydrogels. It's one of the chemistries we have more, but this is based on using tri-block polymers. You have a bottle brush block, and you have linear blocks here, and these linear blocks at the end are thermosensitive, and specifically we use this polynipam, and this block is has a low critical solution temperature. So if you go increase temperature at room temperature, it's you have a dilute solution. But if you go to reaches temperature of the body temperature, then you have microphase separation, and this polynipam. You have this formation of domains, and effectively these domains play a role of a crosslinks, physical crosslinks. And this is an example of one of the chemistries that we're using to make these macromolecules. So in this, this is hydrogel. Both blocks are hydrophilic. Only NIPAM would phase separate and at 37 degrees. So, and using this chemistry, or this type of macromolecules, we can control this phase separation temperature. But for example, what we do here, we just basically tune vary this degree of polymerization of the linear block. The bottle brush block, it's a polyethylene glycol block, is constant. We do not change this. We only, let's say, change this degree of polymerization of the linear block or volume fraction of the linear block. And as we increase it, you see that it's phase separate or gelate, because of gelation temperature, the material gels at a lower temperature, basically. This is number one. And it's also, but it's again, it's around body temperature. It should be before 37, it's fine. So it's not that important, but what more important is that also using this architecture, and we can control modulus in a very broad range. What is shown here, it's a modulus measured at 37 degrees. It's at the body temperature here. And again, this is plotted as a function of volume fraction of the linear block, or effectively it could be a degree of polymerization of the linear block here. And the second parameter is the concentration of the solution, 5%, 10, 20%, 100% would correspond to a dry polymer here. So, but using combination of this architecture and volume fraction concentration of the solution, we can control modulus within, let's say, almost 5 orders of magnitude, which is again very significant. And we can match any modulus of any tissue. But the issue here is pay attention that you see we use this, we change concentration of a solution 5%, 10, 20, but in real tissues, the concentration of whatever protein or macromolecules is around 30%, and 70% is water. 70% is water. So it means what we have here, it doesn't correspond to to equilibrium concentration of and material. If you inject it, what can happen? This material will shrink, or they may swell uncontrollably. So basically, the next step we wanted to understand: can we control this decouple swelling ratio and mechanical properties? Yeah, but before we'll talk about it, I just want to demonstrate that these materials are very resilient here. This resilience on the right-hand side shows, for example, by compression, you compress it by a factor of 5. So this is, even so, this is a physical network, but they can withstand compression more than by a factor of 5, which is again important if you intend to use it as implants, body implants. And this is also similar, but it's a shear stress, and it shows that it can withstand up to 300% of shear strain. And also, if you do extension tests, it doesn't have, I mean, complete kind of matching of tissues, but it shows that it has significant strain stiffening. So we're very close. Okay, but it's. And also there is, to demonstrate different applications with this system, we can do 3D printing. We also show that materials are non-cytotoxic, and they do not cause any inflammation here. And also this, it's nice, it was initially designed to basically add a red color, which would be rhodomin B, just to simply demonstrate that as you inject it to a water, to a vial with water with 37 degrees Celsius, and you have immediate or prompt gelation here. But then looking back, we said, oh, look, what is interesting here is that this is rhodomin B, and rhodomin B is a hydrophilic molecule, and it's why does it stay inside this hydrogel? Why this solution of water didn't turn pink? And this is something interesting, and we're looking now very closely because it's quite unusual. So you're adding hydrophilic dye, which stays inside in a hydrophilic polymer injected into water. So it's quite important for drug delivery. So now back to this fundamental question: how can we decouple modulus and swelling ratio? And this is an illustration of this interesting paradigm that if you take our body, there is a lot of different tissues And these tissues have different modulus, and the variation of modulus is up to, let's say, 5, 6 orders of magnitude, what is shown here. But all these tissues have the same water concentration, 70%, around 70%, but modulus is in nature knows how to decouple, how to control change modulus at a constant composition. And if you take polymer networks, I mean, every polymer scientist would know this, and again, I already talked about it, that the swelling ratio is it's a volume of the gel divided by volume of a dry material, or dry polymer, and it's equilibrium swelling ratio. This is directly related to modulus. I mean, because both parameters are coupled through cross-link density. So it means if you increase modulus, you decrease swelling ratio, and vice versa. If you make softer networks with low cross-link densities, this modulus would decrease and swelling ratio would increase. So all of them would fall on this line. So but this is not how nature works. Nature works, it is able to stay on the same swelling ratio, the same amount of solvent, and vary modulus here. And this is, we believe we can do it with brush-like networks, because if you control, let's say, if you change cross-link density, I mean this NX, it's a degree of polymerization of the backbone. In this case, it will be very similar behavior like with the linear networks. But if you keep constant degree of polymerization of the backbone and change degree of polymerization of the side chains, you will have a different behavior. You will decrease modulus, material becomes softer, but it becomes also, it swells less. So basically, I will show you, I will explain you the reason for this. But effectively, what we will do, instead of this following this one-dimensional line here, with this architecture, which we can cover an area modulus versus swelling ratio. So it means we can stay at the same swelling ratio and can synthesize materials with different modulus. So this is the goal. So why this happen is just because this is at the top, what you see, it's a linear network, and then you start adding side chains and increase length of the side chains and add more side chains. Basically, you go to this bottle brush architecture. So as you do this, two things happen. First of all, your strands becomes bulkier. As they become bulky, effectively, you decrease cross-link density, so it means materials become softer. But also, if you increase cross-link density, grafting density, due to the steric repulsion between densely grafted side chains, the strands will extend. So basically, as the strands extend, you kind of enhances firmness. So, and in order to visualize it, you can do the stress-strain experiments, elongation experience, for example. If you take linear networks, and if you change, there is only one parameter to change. It's just cross-link density or degree of polymerization of the strand here. So if you increase the strand length, basically you decrease cross-link densities, then you have this modulus decrease. Basically, you have this very conventional behavior. But with brushes, it's different. If you keep, for example, constant, relatively constant, let's say, degree of pension of the backbone and increase side chains, what will happen? The networks become softer, but they become firmer. You have this enhancement of the strain stiffening. And again, these numbers in brackets gives you this first number is the degree of polymerization of the side chains. This is degree of pension of the spacer between side chains. The degree of polymerization of the backbone. And basically, you go from if you go from left to right or from bottom to up, then you effectively go from bottle brush architecture to comb-like architecture and to linear architecture. Basically, you remove side chains here. And as you see, as you do this, and they become stiffer and also, but less firm. So, and as a result, so basically you have materials which have different models, but they intersect at the same, let's say, deformation and the same stress. And this is what effectively corresponds to this, the same swelling ratio. So anyway, so to check this hypothesis, what we synthesize polybutyl acrylate networks. So you have the side chains, you have cross-link, you have space, and important in this chemistry is that to make this consistent, reproducible, you need to make sure that side chains, backbone make of the same materials. In this case, all three components, side chains, backbone, is made of crosslink is made of the same polybutyl acrylate chemistry. In weekend architecture, we can control in very broad ranges here, architectural parameters. All right, and this is basically a kind of summary of the study. And well, it's very simple conclusion. On the left-hand side, you see different architectures, different, first parameter is the degree of permeation of the side chain here. This is crosslink density. And you get different architectures here, starting from linear to bottle brush. And these different architectures have the same swelling ratio, equilibrium swelling ratio around 14. It means 14 times expansion of volume, but they have different models here. So what you see here, this has very soft 1.4 kilopascals, but basically you have a 10 times variation models at the same swelling ratio. And we, of course, did many architectures, and we can plot them modulus as a function of swelling ratio. We have a system of these curves, parallel lines, but again, the conclusion here is that, for example, we can stay at the same, maintain the same swelling ratio, and only change architecture without changing chemistry, only architecture, and we can change modulus by, let's say, 1 order of magnitude here. See, this is what we discussed before. If I go back, we're talking about covering this area here. So this is nice, and in addition, if you you notice that this is swelling ratio is 14. Is not what is not. The swelling ratio is much higher than tissues because tissue has 70% of water. It means swelling ratio effectively 3, very low swelling ratios. To control swelling ratio, we can mix different type of side chains, hydrophobic, hydrophilic, and as you add, let's say it was polyethylene glycol, we can control fraction of the hydrophilic block, and in this way we can control the concentration of water uptake. In addition to architectural control, we can also add this compositional control here. And if you have, for example, 5 weight percent of polyethylene glycol side chains, we have 10% water uptake. This is about 15, and you increase concentration, molar fraction of PEC side chains, and you increase water uptake. So I think this is with this are probably, and also but as you change this water uptake, you do not change modulus much because modulus is controlled by architecture. As you see here, go from this is pure PEC, pure butyl acrylate, and this is copolymers, and you basically traverse from one line to the other. You change swelling ratio significantly here, but you do not change much modulus here. So it's nice. So with this, I think I would like to finish, and I would like to thank you to my collaborators on the right-hand side, and to my students and postdoc, and to funding from different sources. And of course, thank you for your attention. Thank you.
Thank you very much for interesting talk. And we have a little bit time for discussion. Let's have one question. In Zoom, maybe?
Yeah. Do you hear me? I have a question.
Mm-hmm.
Yeah, I don't know, my video disappeared. So if I look at this behavior, so it's very fascinating how the strain hardening happens in these systems. If I compare the system, say, to cytoskeletal network, and if I make a simple model, so that doesn't have the bottle brush structure, if I let the little strands to interact and then form crosslinks, they can be myosin or something else, but if they can break and form, I get this kind of extreme strain hardening the same way. So does this behavior have anything to do with your networks?
Yes and no. I mean, definitely biological biomaterials in general, they have completely different molecular structure. And this strain stiffening behavior comes from this collagen network, and collagen, you know, this has hierarchic organization. It has this microfibrils, microfibrils, and you have this triple helix. And as you stretch, you basically have a cascade of different molecular mechanisms at different stress levels. And initially, if you take collagen networks, what you do first, you kind of unfold or this collagen without stretching them. They basically change conformation, and this is a very low energy process. It's because it's a persistent length of collagen is very high. To just unbend it, you do not need much energy, and this is why you have initially low stress or low modulus. But then as it completely extended, now you have the sliding of those microfibrils, you break these hydrogen bonds, etc., etc., etc. So it's this type of mechanism. In our case, as I said, it's different, but it's similar. Similar in a way, if you take these bottle brushes here, they also, like maybe in this cartoon is better, they also kind of bend, they're not straight. And then because it has a very bulky structure, large diameter, it's similar to collagen, they have relatively low persistent length. So it means it's also very easy to extend them. So you extend these bottle brushes and give you low modulus. Then as eventually they become fully extended. And then what happens? You start extending backbone inside bottle brush envelope, because backbone is not a good cartoon here, but backbone here is not fully extended. Backbone also coiled here. And then, and when you extend backbone, this is a very high energy process because you, it's again, Kuhn length will be much lower for backbone, so it costs much more energy. So this is, and then if you talk about physical networks like we discussed here, the third mechanism would be you would extend these linear blocks from these domains, and this is another much higher energy process because you need to pay this interfacial energy price. So it's also what I said is completely different, but in a way is similar because it's also cascade of different molecular mechanisms important inside the same strand. It's not like you have two networks or interpenetrating networks with low or high cross-link density. It's the same network, but within one strand, similar like in collagens, you have a cascade hierarchical structure with a cascade of mechanisms. So this is our current interpretation.
Okay, and if I may continue, so where I had the picture with the red dots where you have the crosslinks. This may be a silly question, but if you would change, say, the distance, let's say in the horizontal direction versus the vertical direction of the density, would you get orientational response that would be different? What do you think?
Orientational is, oh, well, if you make some anisometric or anisotropic network, and you see this strand will be shorter. Yes, it's a very good question in general, because we know that tissues has an anisotropic mechanical properties. I mean, if you take a tissue in different directions, they show different modulus. And yeah, I mean, we're interested in making our brush networks also with this type of properties. But I think not, I'm not sure whether, because still it will be, network will be isotropic. I mean, it will be averaged. I mean, if you have short and long strands, I think the response will be average. But I think there is different ways to create anisotropic.
Right, but the entropic elasticity would be quite different in the two directions, right?
Well, I mean, in this schematic, when you look at this cartoon, but if you take a real network, it will be, everything will be disordered. No particular order with respect to a particular direction. All right.
Thank you.
Sure.
Okay. Thank you very much. Is this all questions?
I have a question.
Yes.
Well, this is Hector. I have a question. You mentioned during your talk that actually the chemistry of the side chains doesn't play a real role on all these systems. How can you explain that, or is this only for non-polar or not polar or just polar? Because I will expect that for the side chains, especially crowded side chains, if they would be charged,
right,
play an impact.
It's a good question. I mean, yes. No, first, let's put aside this molecular structures with specific interactions like hydrogen bonding and ionic interactions. There is a large family of polymers or materials with hydrophobic, I mean, just organic molecules, polystyrene, polyacrylate. There is no any specific interactions. And my comment was more related to this type of, so it really doesn't matter if you take polyethylene glycol, polybutylacrylate, polystyrene or whatever. I mean, this still, it is like this. If you change chemical composition of a polymer network, of course, modulus will change. It will change maybe by a factor of 2 or 3, which is in principle significant. You change modulus by a factor of 3. But if you change architecture, you change modulus by 3 orders of magnitude. It's a different level of control. My point is like this: with this level of architectural control, I can always take 3 different compositions, and I can always find a set of parameters, architectural parameters, that stress-strain response of chemically different network will be completely identical. My point is this architectural control overpowers this chemical control. So, and actually we have, I don't have this slide with me, but I have, let's say, polybutyl acrylate, polydimethyl siloxane, polyethylene glycol, and polyisobutylene with identical stress-strain behavior, but a slightly different architecture.
So if, no, thank you very much, actually makes sense. Just one question. So for you would not make sense at some point if it would be synthetically possible, because I understand that your polymers are much easier to deal with, but if you could actually use some native glycans, which are of course rich on OH groups, hydrogen bonding, will you get all this, another level of all this breaking and forming all these bonds? Will it make sense, or it just simply does not pay off because you can access to these different scales without actually having to complicate your life with the chemistry of sugars?
Right. I mean, yeah, it all depends on, of course, on length scale, but actually nature does it. You mentioned protoglycans. This is effect brush my macromolecules, and I believe nature designed this on purpose to control mechanics. I mean, if you take our cartilage, it's exactly, I mean, compressibility and friction, lubrication properties are controlled by this, by brush-like architecture. Yeah, and then, yeah, the natural molecules, you have hydrogen bonding, you have also, this is polyelectrolytes, but I think polyelectrolytes, ionic interactions are screened very much at body conditions, so you can consider them neutral. But yeah, you have specific interactions. I guess they're essential, but they will change, of course, they will affect mechanical response. In this case, they may be as strong as, like, say, as architectural control, but I guess
it was just to know. It's just don't worry. I understand that that's a difficult question. Anyway, thank you very much. It was a very nice presentation.
Thank you very much.
Thank you.
Okay. All right. Am I good to go?
We're missing the sound. Coffee break by the other schedule.
I'm sorry, we have some problems with microphones. So thank you very much for your interesting presentation. And now we will have some small coffee break for
Thank you.
10 minutes.
our studies of interactions between cellulose-based materials and skin. And first of all, I would like to say a couple of words about cellulose itself. As you all know, cellulose is a polysaccharide which comes from natural sources. It's everywhere, and in fact, it's the most abundant organic material on our planet. And because it's easily accessible, it's very cheap, but at the same time, it has very important and unique properties. It's biodegradable, biocompatible, non-toxic. So therefore, not surprising, this cellulose-based materials are widely used for medical and biotechnological applications. Just to name a few, cellulose is used for wound dressings, bone implants, tissue engineering. The first hemodialysis membranes were also made of cellulose. And whichever application field you take for cellulose, at some point the cellulose material should come to direct contact with living tissue or skin. And at this point, we would like to ask ourselves at least a couple of questions, very important questions. First, what would be the impact of cellulose on living tissue and skin? And the second, and I would like to focus on the second question in my talk, what would be the interactions between cellulose-based materials and living tissues, the molecular mechanism of these interactions, and if you know these interactions, whether we could control these interactions, whether we could, for instance, weaken them if we want to. My talk today will be devoted to the use of cellulose-based materials for wound dressing, and of course, if we speak about wound dressing, we keep in mind the interaction of cellulose with skin, or more precisely, to the outermost layer of skin called stratum corneum. So in this nice paper, I found this nice picture of a structure of stratum corneum. Briefly, it has a very familiar, very well-known brick and mortar arrangement. Bricks here are corneocytes. In fact, they're just basically dead cells, so they're very impermeable, and they're all surrounded by the lipid matrix. Lipid matrix has a multilamellar structure, which is basically just a stack of lipid bilayers taken together. And these lipid bilayers constitute of three major components, three types of molecules: ceramides, cholesterol, and free fatty acids. So we would like to consider stratum corneum, and yes, the lipid matrix, this is the only permeation pathway for the skin. So whatever you want to, for instance, deliver from the skin, you need to affect on the stratum corneum, so on the lipid bilayer. And so these lipid bilayers of stratum corneum we will consider as a model of stratum corneum in our simulations. So we focus on the interactions between cellulose crystal and the lipid bilayer of stratum corneum. And because we're interested in molecular picture of interactions, we will do atomic scale computer modeling, atomic scale molecular dynamic simulations. So now I invest a little bit more words about the objects themselves. So first of all, this is a cellulose crystal in the way we use it in simulations. So basically, this is very small piece of cellulose crystal. In here, we have only 3 layers. And this is basically not very important because what we're interested in the interactions of the surface of cellulose crystal with anything which comes in contact. So we don't really interested in the interior of the crystal. So we could, in simulation, take the whole inner crystal structure frozen. So we're allowed to move only the hydroxyl groups which are on the surface of cellulose, the rest is just frozen. As for the stratum corneum lipid bilayer, as I said, there are three major components, types of molecules, which we can find in this lipid bilayer. They are ceramides, cholesterol, and free fatty acids. Well, cholesterol is unique. There are no discussion here. However, it comes when to ceramide, you can find up to 100 different types of ceramides in skin. So we decided to talk just one. Of course, this is the most abundant type of ceramide molecules you can find in the stratum corneum lipid bilayer. It has this strong, this long name, but important thing is that there are two lipid chains or this lipid. Both of them saturated chains. One is 24 carbon atoms long, another one is 18, and the third component is free fatty acids. Again, we take here the most abundant fatty acid found in stratum corneum. So we consider lignoceric acid. The length of the tail of the acid is actually the same as the length of the longest tail of the lipid. What is very important about the free fatty acid? This free fatty acid could be in two states in the stratum corneum, depending on the environment. So it could be protonated and deprotonated. So in deprotonated state, you have charge -1 in here. So basically, this is an ionic molecule. So when this molecule is protonated, basically you have a neutral molecule in here. And all these three components, we consider ternary mixture of these molecules, and we take equimolar mixture. So we have the same number of all these three molecules in our stratum corneum lipid bilayer. So this is the system we are about to study. But before I go to the actual simulations, I would like to mention that there is a fundamental problem with the system when it comes to molecular dynamic simulations. So if you would like to simulate lipid bilayer interacting with the solid cellulose crystal, because of periodic boundary conditions, there is a problem basically, because we apply periodic boundary conditions in all these in all three directions, and when you immediately find that there is no possibility for the lipid bilayer to approach the support, because water permeability is very low. So basically, water does not allow for the lipid bilayer approach the solid support. And it's very interesting to look at the literature. Say there are some thousands of simulation papers on lipid bilayers, freestanding lipid bilayers, but when it comes to the lipid bilayers on a solid support, you can find just a dozen papers. So we looked into this problem some time ago, and the solution is relatively simple. So basically what you need to consider the cellulose crystal of finite size, and the size of the crystal should be a little bit smaller than the cross-sectional area of your simulation box. So in this case, as you can see here and here, there is some room for water molecules to approach the contact area and to leave the contact area. So this way, when considering this setup in our simulations, you can basically move to these objects with respect to each other. Okay, so now the methodology is there. We just take it and apply it to the system of our interest in here. Here we considered the phospholipid membranes. Now we extend it to the stratum corneum lipid bilayer. And here some simulation details. We use charm force field to describe all the components of our system: cellulose crystals, ceramides, cholesterol, and fatty acids. What is important about fatty acids is that, as already mentioned, it could be in two protonation states. It could be either protonated or deprotonated, depending on the pH level in the aqueous solution. We looked at the literature, and it turns out that people by far considered only two limiting situations. Most studies in the literature concerned the this lipid ballet of stratum corneum in which all fatty acids were protonated. So it's 100% of protonation, meaning that your whole lipid ballet is uncharged. And just a few papers actually addressed the effect of charge. So they considered the opposite situation when the protonation level is zero. You've got all your fatty acids deprotonated. They're all anionic. So there is very large charge basically on the lipid ballet. So this situation you can find, for instance, in when you go deep into the stratum corneum. So in layers of stratum corneum has a deprotonation level around 100. However, in our classical molecular dynamics simulations, we can't actually change the protonation on the go, on the fly. So we need to decide beforehand what protonation level would be in our simulations. So we decided to sample the protonation levels from 0 to 100 with a step at 25%. I considered five different systems with different level of protonation of fatty acids, and it's altogether we have 5 systems, and we would like to know how the protonation level of fatty acids will affect the interactions of lipid ballet with cellulose. So here's the main result of our study. This is the free energy of binding between cellulose crystal and stratum corneum lipid ballet. So here I showed the distance between center of masses of ballet and crystal. So as you can see, for instance, the black curve corresponds to this protonation level equal to 100. So this is the uncharged membrane, and you can see that there is very large minima in the free energy of binding, meaning that we've got attractive interactions between cellulose and lipid ballet. So then we start to decrease the protonation level from 100 to 0. So I move from bottom to the top. And you see that the depth of the wall continuously decreases. And say at 50%, we still have some wall here, well in here. So meaning that we still have some attractive interactions between these two objects. At the protonation level less than 50%, so there is no well on the free energy profile. So the object should basically experience repulsion, electrostatic repulsion with respect to each other. So there is no binding for these two systems. These results are without salt, just with count ions. Of course, every time you have charged species in the simulation, you should check the effect of salt. So we've done that. We added salt, the potassium chloride concentration, physiological concentration, 150 millimole. It turns out that, of course, what you expect from salt just screens the charges of the lipid ballet. So the crystal feels the charge of lipid ballet on smaller distances. For instance, black curve here, this is the curve without salt. The cyan curve here is situation when we added salt. So you see that cellulose fills the membrane at smaller distances, but when it approaches it, we still have we still have a minimum in the potential of mean force, meaning that basically our main conclusions stay the same as here. So basically we can conclude that this picture will also stay uncharged when we add physiological concentration of salt. Okay, this is all about unbiased, so it's all about biased simulation. These biased simulations predict that we basically could expect here the attraction for these three systems, 100, 75, and 50. and we go for less, for smaller protonation level, we should expect repulsion. So now let us look at unbiased simulation. So we have these two objects here. We put them together and start a simulation. So and you can see without any bias. So you see that the binding basically occurs for these three systems as predicted by the three energy profiles. So these objects are at large degree of protonation of fatty acids that basically stuck together and they're together for the during the simulation course up to 600 nanoseconds in here, but doesn't matter actually how long. And these two systems, when there is a small number of fatty acids protonated, they basically we see repulsion between these two objects. So basically we see the confirmation from the confirmation of our finding from unbiased simulation as well. However, now we have three systems which are bound together without any bias. So we could actually look what kind of interactions they experience. And here we could take the advantage of atomic scale molecular simulations that look precisely what happens in our system. So to do that, I just plot here the mass density profiles for different components of my system. So red is for cellulose, black is for stratum corneum balea, and actually also showed some components inside of within the stratum corneum balea, like for instance ceramide shown by green and so forth. So you can easily see what kind of molecules basically come in the contact with the cellulose, which is shown in red. So first of all, seeing that the ceramide basically participated in these interactions. On the other side, if you look at the cholesterol is located deep into the lipid balea and basically does not participate in binding at all. And then there are two types of fatty acids, the deprotonated and protonated. So here the protonation level is 50%. So you see that the deprotonated molecules are closer to the interface, meaning that they interact strongly with the cellulose. And the explanation here is that they basically pulled towards the interface by the counter ions which are adsorbed on the surface of membrane. When we increase the protonation level, so the picture stays the same with the exception of the fatty acids. So fatty acids now, so you see the protonated fatty acids, they also approach the interface. So this means that the protonated fatty acids also participated in interactions of balea and cellulose surface. And here this picture for the situation when we have only protonated fatty acids, so the fatty acids participate even more in the interactions. So now we would like to ask ourselves the question about the nature of interactions. And if you look at the chemistry of these molecules, this is the cellulose dimer and ceramide, cholesterol, and fatty acids. So in this particular case, we have the usual suspect. This usual suspect is hydrogen bonding. Indeed, there are some hydroxyl groups on the surface. There are 3 hydroxyl groups on the surface of the cellulose dimer, and there are also the hydroxyl groups on the head groups area of ceramide, cholesterol, and the protonated fatty acids as well. So we just calculated the hydrogen bonds between cellulose and baleas for 3 systems in which we have tight binding. So you see, indeed, so these numbers are the number of hydrogen bonds per cellulose dimer. So they do not really depend on the size of the system. So you see that the numbers are large for the total number of hydrogen bonds between cellulose and bilayer rather large, and increases when we increase the protonation level. Now, if we look at the contributions coming from different types of molecules, so first of all, as we expect and as we see from us density profiles, so major contribution to the hydrogen bonding comes from the ceramide. So cholesterol does not participate at all, so the numbers are very, very small. And as for fatty acids, the situation is more interesting. When the protonation level is 50%, as we saw from mass density profiles, major contribution comes from deprotonated fatty acid. When for the system at 75%, both fatty acids contribute equally to the hydrogen bonding. And in the situation when only protonated fatty acids exist in the system, you see that basically every third hydrogen bonds in the system are provided by the protonated fatty acids. So the contribution is quite large. Okay, so some preliminary results which I can basically draw at this point is that we've done molecular dynamic simulations of these systems, and we determined two major factors that control the cellulose-skin interactions. First factor is the electrostatic repulsion between cellulose crystal and deprotonated fatty acids. So, and second factor is the cellulose stratum corneum hydrogen bonding. So one leads to attraction, another leads to repulsion, and the interplay of these two factors basically will should show us some particular behavior. Say when we have less than 50% of fatty acids protonated, we see the repulsion. Repulsion dominates, and there is no bonding between skin and cellulose material. Otherwise, when the protonation level is higher than 50%, then hydrogen bonding basically dominates, and we have tight bonding. So this is very nice results in terms of simulations. However, it's very interesting to link them to the real system, to the real stratum corneum. Okay, let's look a little bit at the real stratum corneum. It's known that on the surface of our skin there is acidic mantle, meaning that on the surface of our skin, of our stratum corneum, the pH level is from it's acidic, and it is in this range 4.5, 5.3 in the outer layer of stratum corneum. When you go deeper to inner layers, the pH level becomes almost neutral. And now the interesting question is about the pKa of the fatty acids we used in here. I recall that this is the most abundant fatty acid in the stratum corneum. So the pKa of lignoceric acid is 4.95. So in principle, approximately the pKa of fatty acids is more or less the same as the pH on the outer layer of the stratum corneum. When pH is equal to pK, we have 50% of fatty acids protonated. So now we go to our results and we check them, and we find out that it should be binding. So in principle, if you've got crystalline cellulose, unmodified pristine cellulose, and you have a healthy skin, it should be binding of cellulose material to the skin. So this basically knowledge comes directly from the computer simulations. So the main conclusion is in here is such that if you would like to weaken the adhesion of the cellulose material to the skin, we need to increase the pH level in the cocktail area. So this makes the bilayer more anionic and increase the electrostatic repulsion between stratum corneum, lipid matrix, and cellulose. This is the main conclusion. Okay, the publication of this paper, the paper was published in Soft Matter, and appeared on the cover of the journal. So it's very nice cover art made by Mika. And finally, I would like to acknowledge, of course, contribution of my close collaborator Mika Kartunen, the financial support of Russian Ministry of Education and Science through the Mega Grant program, and we used Compute Canada facilities for our computer simulation. So at this point, I stop and thank you for your attention.
In Zoom, maybe?
I can ask a question if nobody else has to start.
I'm sorry. Yeah.
Oh, do you hear me?
Okay. So actually,
Okay.
I have a question. Andrei, you use equimolar ratio of components in the lipid bilayer, but on the scheme that you show on the second slide, maybe it seems that fatty acids and cholesterol are minor components in lipid bilayer, and in picture they are less than lipids. But no, on the second slide here, no, further on the fourth. No. Here, it seems that fatty acids and cholesterol are minor components. There are less amount of them in the lipid bilayer, but in this case, why equimolar ratio? Or maybe just scheme, I don't know.
Well, this I guess this is just a schematic representation. Of course, the composition of real stratum corneum lipid bilayers they vary depending on the species and so forth. But most commonly, people consider equimolar mixture as a model of stratum corneum lipid bilayer. So this is I think this is a better impression just from this scheme. So, and you also should take into account that fatty acid has just one tail and the lipid has two tails. So maybe there are too many tails of lipids in here. Okay. So I suggest you look at this picture instead.
Yeah.
Okay.
Okay. Any more questions?
Yeah, I have. Do you hear me?
Yes.
Okay. Does Andre hear me?
Yes.
Yeah.
Okay, good. Hi, Andre. So let me ask a quick question. So what do you think, how important is this the dehydrated environment? And secondly, the pH gradient that's in the system and the outer layers?
Well, we pH level basically. So if you go deep inside, so your pH level basically will increase, and the number of deprotonated fatty acids will also increase. So of course it's important. So if you go deeper, say if you have some trauma, you have some broken say stratum corneum, and you apply cellulose material on this wound. So I think when you go deeper, your repulsion will be stronger. So maybe it's a good thing. Dehydration, I think it's hard to say, because when you have a small amount of water molecules hydrating the head groups, so it's not very clear for me, for instance, how it will affect the pH level. Yeah, so maybe it's worth to look into it.
Thank you.
Let's see.
Oh, Andrei, I've got a couple of questions. So first one is about preparation of your initial configuration. Do you need some special trick when you prepare the initial configuration of your membrane? Because the system is multi-component, so one, I suppose, need to prevent aggregation of similar molecules. Or so my question: do you need some special tricks when you prepare your stratum
So
corneum?
we did in the past. Now we have Charm GUI. It's online membrane builder. You basically just define what kind of membrane you want, what kind of components you want, how many of them, and then you can prepare it automatically on the fly. So what Charm GUI provides for you basically is more or less well calibrated, but we still for mixtures we need very long times for equilibration. So at least I pre-equilibrated this these lipid ballets for at least 1 microsecond, just to make sure that everything is fine with mixing of lipids. That's it. So now it's easy these days, especially if you use Charm.
Okay, and thanks. And my second question is about slide number 11, the free energy curves. So at 100% protonation, you see that you you fall in the minima, while at say 50% or 75%, this minimum at small distance is separated from another broad minimum by some barrier. So in fact, you have.
Okay. Yeah. You mean this?
I mean this barrier on green and blue curves. Does it have some special meaning? This bimodal structure.
I think the meaning of that is that when the ballet approaches, the ballet approaches the cellulose first. So what cellulose feels is a negative charge of the surface. So on black curve, this is the situation when there is no charge. Okay, so these 4 curves corresponds to charged lipid ballets. So lipid ballet approaches the cellulose, and what is seen in here, this growth is because of electrostatic repulsion. But then at some point there is hydrogen bonding between cellulose and lipid ballet, and then you've got basically the opposite effect. You've got a direction to the minima, and that's why you've got this kind of maximum in here. Okay, but partly this maximum is also from the because we do not consider basically the salt. So if it will be salt, but I think for salt I think it's the same. Yeah, as just said. So you approach the surface. First you have repulsion, but when there are some hydrogen bonding, this hydrogen bonding rather strong. The hydrogen bonding is stronger than repulsion, and you've got a minimum. In this case, for instance, for the red curve, you've got the repulsion, but the hydrogen bonding is not enough to overcome this repulsion, so there is no maximum here, and there are minima here as well. So I think this is the physical meaning, as far as I can see.
Yeah. Okay. Thank you very much.
Thank you very much. So I suggest to go to next speaker. Next speaker is Mikhail Smirnov from our lab, Institute of Macromolecular Compounds.
Materials. And here is a small plan of my. I want to focus on the mechanical properties and application of cellulose nanomaterials to demonstrate why they are important, and then I will discuss the literature data about the structure of deep effective solvents to get more insight in their properties, translation between structure and possible. And after that, I want to explain general ways for production of cellulose nanomaterials and to demonstrate. Okay. So mechanical properties of cellulose nanomaterials. It is reported in literature that cellulose nanomaterials demonstrate, highly crystalline cellulose nanomaterials demonstrate very high mechanical properties which are comparable to the Kevlar fiber in axial direction. So they have higher elastic modulus and also comparable, I think this is mistake, there are megapascals, comparable strength with other fillers which used for reinforcement. These are the properties of crystalline cellulose, but biomass consists of a lot of some subproducts, not only crystalline cellulose, and the main idea of cellulose, of production of cellulose nanomaterials, is how to separate this highly crystalline material from hemicellulose and lignin. Here presented some application of nanocellulose. So most of them are, maybe all of them are in from our laboratory, from our cases. So nanomaterials are, cellulose nanomaterials, a lot of use of them is connected with the reinforcing of polymer composites, like in the first corner. So cellulose nanofibers here can interact with each other through hydrogen bonding and form very tight network, which result in the very strength composites. The next idea for using of cellulose nanomaterials is also connected with their mechanical properties and their inter-fiber interaction. When we introduce cellulose nanofibers in some solvent, we can regulate rheology of this material, also attain shear thinning behavior, which is very useful for 3D printing. Also, cellulose nanomaterials are used in electroactive materials. So here are two examples: reinforcing of electroactive ion gels for tactile sensing, and also as a template for porous electroactive materials, which can be used for charge storage devices with high specific capacitance. So, and here are the second players of the story: deep eutectic solvents. So in literature, distinguish 4 types of deep eutectic solvent. Most of them contain metal ions. However, only type 3 not contain, and we will discuss mostly about this type of deep eutectic solvent. This solvent consists of large organic cation and counter-ion for this organic cation. Most often these are chlorine or bromine ions, which can act as Lewis base or hydrogen bond acceptors. And the second component is Lewis acid or hydrogen bond donor, which can be composed of various materials such as urea, different amides, alcohols, and carboxylic acids. So deep eutectic solvent have the name because this interaction between hydrogen bond acceptor and hydrogen bond donor results in very large and complex shaped ions, which have low lattice energy in crystalline state. Thus, they have low melting point, and this melting point is usually much lower than melting points of individual components, maybe usually more than 100 degrees. And here is some example of crystalline choline chloride, crystalline malonic acid, and together when you mix them, they form liquid at the room temperature. So interaction between these components are very complicated, and were the field of studies for a lot of papers. And here I present literature, some summary of literature data which demonstrate how this bond donor and acceptor can interact with each other. Mainly authors emphasize interactions between OH group where delocalization of charge from oxygen to hydrogen of halide chloride. And the next one, maybe the most important in this system, is the interaction between chlorine ion and hydrogens connected with oxygen or nitrogen. And the last one is also interactions between P bond between carbon and oxygen. For example, this bond appears in urea or malonic acid, and with also H atoms of halide chloride connected to the positively charged nitrogen. So I will return now back to cellulose, and here is the brief scheme that demonstrates the preparation, the general road for preparation of nanocellulose from biomass. And this generally we can tell that there are two stages. The first stage is pretreatment stage, which can be chemical, physical, or biological. And the aim of this stage is to eliminate some lignin, gamete-cellulose, and other not cellulose components, and also to make this biomass more porous and more accessible for further penetration of active molecules, which will remove the amorphous parts of cellulose. So in this case, in this first stage, usually acids used for this purpose. After that, the next step was introduction of ionic liquids, which can dissolve lignin and gamete-cellulose. But ionic liquids are expensive and toxic in some cases. So now, more and more extent, are changed to deep eutectic solvent, which have similar physicochemical properties but lower costs and lower toxicity. And the next, so this first step is the main field of application of deep eutectic solvent for nanocellulose production. However, the next step is nanocellulose isolation. So this is removing of amorphous part of cellulose or splitting of cellulose nanocrystals from each other. That results in preparation of cellulose nanocrystals, here up, atomic force microscopy image, or cellulose nanofibers. They are different in dimensions. And mainly for preparation of cellulose nanofibers, physical methods are used, such as high pressure homogenization or high intensity ultrasonication, which can disrupt cellulose microfibers but preserve nanofibers. For preparation of cellulose nanocrystals, mostly acid hydrolysis is used because it allows to hydrolytically remove amorphous parts and retain only highly crystalline areas. And deep eutectic solvent in this second part also can be applied, but examples are, there are much less examples in comparison with the application for the first type. And here is some literature examples for application of this for biomass pretreatment. And authors, as the main benefits of using of deep eutectic solvent, authors mention that the application of deep eutectic solvent preserve crystalline structure, degree of polymerization, and also have high removal yield of lignin. And also, application of deep eutectic solvent allows to increase the porosity and to swell cellulose in some extent, which is beneficial for further isolation of cellulose nanomaterials. So this is examples of preparation of cellulose nanocrystals. So the application of deep eutectic solvent as the second stage for isolation of nanocellulose. So for the case when dipoptectic solvents are the last stage, we found only two works. One of them is ours, and here they are. So the cellulose nanocrystals, these demonstrate that cellulose nanocrystals can be isolated using of dipoptectic solvent, and also that using of more hydrolytic actively oxalic acid results in finer cellulose nanocrystals than in our case. This is the second case of haline chloride-urea. This is our work. But in the case of oxalic acid, the lower degree of crystallinity than in our case, and also in our case we have the much lower degree of surface chemical modification. So I will show this further. This is also some our results. We were interested in the question how cellulose interacts with dipoptectic solvent. So the main idea is that cellulose also contains hydroxyl groups. So cellulose also as a component of dipoptectic solvent can act as a hydrogen bond donor or hydrogen bond acceptor, so it can somehow interact with both of components of dipoptectic solvent. And the results of simulation which was performed by Dmitry Tolmachov demonstrate that cellulose mainly act as hydrogen bond donor. So I cannot show, unfortunately, but the most pronounced interactions are between chlorine ion and in this example oxygen atom from urea with hydrogen atom of cellulose hydroxyl groups. So here are also literature data. So on the idea that cellulose can interact with dipoptectic solvent by the same manner as the components of dipoptectic solvent, rise the idea that it can be used for dissolution of cellulose. So it is somehow questionable, are there exist the true solution of cellulose in these solvents, but anyhow, in literature presented data which demonstrate that cellulose have some solubility in the number of dipoptectic solvent, and interesting in this paper was that authors analyzed the correlation between solubility and some parameters, and they derived that Kamlet-Tafel empirical polarity scale of solvents can help them to understand why some dipoptectic solvents dissolve cellulose better than others, and here are some summary of the results. So also they found that the main parameter which determines the solvent activity towards cellulose dissolution is hydrogen bond basicity values of solvent. So its activity as hydrogen bond acceptor. And this correlates well with the results of molecular dynamics simulation which was performed by Dmitry. This was interesting for us because this allows us to explain some of our recent results, and they are given here. So we, just a moment here. So one part of our work is connected with isolation of cellulose nanofibers from bacterial cellulose. And here is the scheme of preparation of these cellulose nanofibers. This allows us to disrupt this bulk bacterial cellulose with formation of individual cellulose nanofibers gel. This nanofibers as gel can be used further as building blocks for 3D printing or preparation of some composites, which is difficult with the initial bacterial cellulose as a block material. And we, in this process, we study or we control the morphology of cellulose nanofibers with atomic force microscopy, and we found that some dipoptectic solvent which we are using leads to more pronounced swelling of cellulose and other not. So, and here are presented some number of solvents. We use, as a dipoptectic solvent, we use mixtures of acrylic acid with halene chloride, acrylic acid with imidazolium chloride, and ternary dipeptactic solvent, acrylic acid, acrylamide, and halene chloride. So the idea for using of these acrylic monomers as components of this was to introduce the possibility of UV curing to our material, and this allows us simultaneously to prepare ion gel and after that make 3D printing and polymerize it in complex shape. But anyhow, from this atomic force microscopy, from its analysis, it was found that the less diameter was for acrylic acid halene chloride dipeptactic solvent, the first one, and the last one, when we introduce acrylamide, results in the most high extended swelling of cellulose nanofibers. And basing of the results presenting and ideas presented earlier, we can propose that this increased swelling is connected with hydrogen bond basicity, which is higher for acrylamide because nitrogen atom is more active as Lewis base in comparison with oxygen atom in acrylic acid. And this can results in their high interaction between dipeptactic solvent, between ternary dipeptactic solvent containing acrylamide and dipeptactic solvent containing only acrylic acid. So this results in swelling. This is some demonstration of what for we are doing this. Here is the summary of preparation of this ion gel based on polymerizable dipeptactic solvent and cellulose, and after that we use it for 3D printing, and after with preparation of some complex shapes it's possible, and after that this dipeptactic solvent or residual, which mainly halene chloride, can be removed and by simple washing with water, and as a result we have these strong hydrogels which can be used in as injectable implants with where high mechanical properties are needed, and the main proposed application of them is artificial cartilage. So, and here I will return return to the speaking about interactions. So here are results of mechanical properties for the samples, and I want to emphasize two samples. Unfortunately, I can't show, but maybe like this. So this one and this one. This sample, both of these samples are prepared by the same manner of 3D printing, have the same content of cellulose. Only difference is, oh, it started working? No, it's not mine. Only difference is the appearance here of acrylamide, and here is only acrylic acid. And we can see that when we introduce acrylamide, their modulus, elastic modulus, in both measured regions, so 10% and 25% of compression, both elastic modulus decreases, while the strength of the hydrogel increase. So, and this can be explained by the following. So, if when we introduce acrylamide, it interacts better with cellulose. So, the interaction, interfibrillar interaction, cellulose decreases. And this results in the decreasing of elastic modulus because the main mechanism of high elastic modulus of these materials is connected with strong network of cellulose nanofibers. However, from the other hand, this results in their better interaction between matrix, polymer matrix, and filler after polymerization, and this explains increasing of strength of this material. So, and finally, here are some pictures demonstrating the preparation of cellulose nanocrystals using dipeptactic solvent. Here we can see how microcrystalline cellulose destructs in dipeptactic solvent with formation of some smaller objects. So interesting that these smaller nanocrystals have approximately the same degree of crystallinity as demonstrated with X-ray diffraction data. This means that all destruction takes place in amorphous parts, and also chemical structure preserved, and additionally no high degree of surface modification, so infrared spectra are rather similar. And from atomic force microscopy, we found the dimensions of our nanocrystals, and they are presented here. It can be proposed. The following shape can be proposed from this data of nanocrystals. So this nanocrystals was applied as a reinforcing filler for high-Tazan membranes, and this was successful. So the strength increases. So thank you for your attention.
Thank you very much, Mikhail. Any questions?
Okay.
I can ask some questions. I have few. So first of all, you added additional compound in your desk to make to improve mechanical properties, as I understood.
Yeah.
And to improve interaction with cellulose and dissolving of cellulose. My question is, isn't it easier to change anion to improve this interaction due to the fact that we understood that anions is the key of
You mean to change this fluorine atom to on bromide? As I remember, bromide is less active as Lewis base, so I don't think that it will be beneficial. So we need, for this purpose, we need to find anion which is higher use basicity, demonstrates higher use basicity. Maybe it is possible, but I cannot answer. So as I understand, chlorine is one of the most active Lewis base for this case. So, but maybe it is possible, and it's interesting.
important.
I think it is possible. So now we try to find key parameters for this. So this is one of this talk is part of this long story. Not the composition of deep effective solvent is not the only parameter. The another is the style of 3D printing of arrangement of filaments, and Vitaly's poster about this.
Okay. Any more questions?
I have one. You hear me?
Yeah.
Okay. Yeah, thanks for the nice talk. Can you comment on if water is a problem in the network?
Water?
Yeah, so is the presence of water, can it modify it? And in this particular case, like, is there any chance of that?
Yes, I think water can modify the network, and it will change a lot, I think, the structure and the properties. But in this case, we study only anhydrous materials. So, and investigation of introduction of water, of influence of introduction of water is the next step, which is planned on the next year of our study.
All right.
Okay.
Any more questions? Well, thank you very much for your interesting talk. And
Thank you.
I want to notice that we have some small poster session on site. So if you want to look for more works and investigations of our institute, you can go to site and look at the posters, and they have emails. And if you are interested, you can connect after. Thank you very much. And we will continue our conference tomorrow at the same time, 16:30 on Moscow time, and see you tomorrow. Thank you very much.